The Einstein mass-energy equation you often see is wrong.
In the past few days, news about the realization of nuclear fusion energy gain has been on the hot search. I believe everyone has seen the so-called Einstein's mass-energy equation many times in the media, because nuclear fusion experiments are based on the mass-energy equation.
The mass-energy equation is perhaps the most famous equation of the 20th century. But in the public media and textbooks, the common mass-energy equation is wrong. The most common is this. E here represents the total energy of the object, including the kinetic energy and rest energy or internal energy of the object. This m is the so-called relativistic mass of the object, which is considered to be a quantity that changes with the moving speed of the object. This c is the speed of light. However, this one is wrong. The correct mass-energy equation should be that E0 is equal to mc squared.
Here m is the mass in Newton's sense, which does not change with the speed.
C is also the speed of light.
E0 here represents the energy of the object when it is at rest, which is called the rest energy or internal energy of the object. In general, for an object, it does not change.
This subscript indicates that the state of the object is at rest. So let's analyze and discuss why this is correct. Four-dimensional spacetime requirements. In four-dimensional spacetime, the spacetime interval ds squared. Here μ takes 1 to 4. Relationship between proper time d tau and ds. What about four-dimensional velocity? It is u-mo, we write, and this is gamma. So the speed in the usual sense is ui, or I takes 1 to 3. Where this gamma is equal to dt divided by d tau. Then the components of the four-dimensional velocity are. This gamma multiplies. The definition of four-dimensional momentum is p nyo is multiplied by the Newtonian mass, multiplied by the four-dimensional velocity. This is followed by four-dimensional velocity. If the first two items are regarded as relativistic mass, then the following velocity is not covariant. Let's take a look at what physicists have to say.
Different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity.
Einstein hadn't noticed the difference between the two before either until June 1948, when Einstein wrote for the last time on the thorny mass problem. He wrote in a letter to Barrett, author of the book The Universe and Dr. Einstein, for no well-defined moving object, it is best not to refer to other concepts of mass other than the rest mass m. Instead of introducing this m, it is better to mention the expressions for the momentum and energy of an object in motion.
Okun, a famous physicist in the former Soviet Union, made great contributions to the understanding of mass and energy.
He wrote many articles throughout his life strongly advising everyone not to use the concept of relativistic mass.
American physicist Carl Adler published an article in the American Journal of Physics. The title was, "Dad, Does Mass Depend on Speed?" Adler replied to his son, "No." Well, yes, actually, no, but don't tell your teacher. The energy and momentum in special relativity. The space component and time component of the four-dimensional momentum are. Here m, remember to be Newton's mass.
The force in three-dimensional space is the same as Newton's law, F is equal to dp divided by dt. Under the action of force, the object obtains kinetic energy Ek. This following item is very important. This is an item that does not appear in Newtonian mechanics. The total energy of an object in motion is this term. In this way, the total energy is equal to Ek plus the following term. The following term is very important. When the object is at rest, then Ek is equal to 0. Then, E at this time should be equal to the rest energy. We write it as E0, where m is the mass in Newton's sense, which is an invariant. This is the greatest discovery of special relativity. When the object is at rest, it has energy E0, and it is related to Newton's mass m. The space and time components of the four-dimensional momentum can be written as this. Momentum can be expressed in terms of energy. This means that the total energy of an object is a measure of the object's inertia, its mass is not a measure of inertia.
Relationship between total energy, momentum, and mass. We get an invariant.
In the rest reference system of the object, when p is equal to 0, then we have E0 equal to mc squared.
Thus, the invariant is m squared in c squared. We get an important relationship between energy, momentum, and mass.
The energy momentum here is meant to be conserved, but the mass is a constant item, and the mass is no longer conserved. In the special theory of relativity, we only use one mass in the calculation of all mechanical processes, which is the mass of Newton. There is no need to quote the concept of relativistic mass. In fact, modern physicists, especially serious particle physicists, do just that, without using the concept of relativistic mass at all. Mass, like charge, is an invariant.
Like the Green-Gordon equation, the Dirac equation, these four-dimensional covariant equations, the mass is an invariant. Moreover, there is no physical experiment that directly verifies that mass depends on speed. Some people may say that we used the concept of relativistic mass to do calculations, and did not find any mistakes. Yes, in general, introduce a quasi-quantity into the theory, and if the calculations are done carefully enough, the results should be the same as the original theory. In a higher sense, however, the theory is broken after the introduction of quasi-physical quantities, because its symmetry is broken. Energy and momentum can constitute a four-dimensional vector. However, if we let the relativistic mass is one component of a vector, what are the other three components?
That's why when people apply those wrong equations, they don't find wrong results, but the symmetry of the theory is broken.
In addition, the introduction of a quasi-physical quantity will affect the understanding of the nature of nature.
For example, the caloric theory that was the mainstream theory before the 18th century, also known as caloric theory, is like this. The reason why I made this video to correct this understanding of the public is also because this wrong equation will also lead to many misunderstandings and debates in physics and philosophy. The mass problem is a very basic problem, but it is also a complex problem.
In order to let everyone know more details,
we will be making a series of videos later on discussing physical and philosophical topics related to mass, energy, inertia, and matter.
Welcome to subscribe.